So this is the chapter 16 through 18 test review. We're going to try things a little bit different. I'm going to get to see me write on paper, see how this video works out. So if you have some comments for me, just let me know how it works out. So today we're doing chapter 16 through 18, which has a lot to do with static electricity and charge generally and what it does to itself and to other charges around. This first question, it's quite from chapter 16. That's what that 16 means. It says, how much force is there between two electrons at a distance of 5 micrometers? So we talk about force between two charges. We're talking about Coulombs Law, which of course is F, let me try that a little bit, there you go, equals K Q1 Q2 over R squared. And so as we look at this formula, we know that K is 8.988, E positive 9, that's always the same. Our charge, those Q's, this is they're both electrons, so they're both going to be negative 1.602 E negative 19. And of course the radius is the distance between them, which is our 5 micrometers, and that needs to be squared as well. So for kind of showing what we're going to do here, we'll take our 8.988 E9, we're going to times it by a negative 1.602 E negative 19. Now technically, because it's the same thing, I could just square this, but I'm just trying to make sure I'm thorough as to using the formula. If you change a couple of things, you can't always square, so it just depends. Now in the denominator, you do always square. That's going to be 5 E negative 6, and we're going to go ahead and square that. So now what we need to do is go ahead and make that calculation. So we'll do that over here in our handy dandy calculator. We're going to start with 8.988 E9 times, and I know that the 1.602 E negative 19, they're both negative, so it's going to come out positive, and it's going to be squared. So here I'll go ahead and type in 1.602 E negative 19. One of the things I love about the scientific notation on the calculator is you don't need parentheses. It should know exactly what to do with that. And then we're going to divide that by 5 E negative 6, and that also needs to be squared. When we do, we end up with a number that tells us the total force is equal to 9.23 E negative 18 newtons, which is not a very big force. In terms of sig figs, the only thing you were technically given in this problem was a single digit, so we would have to make this 9 E negative 18 newtons if we're going to go for sig fig purposes. Alright, question number 2. What electric potential would be required to set up an 1800 Newton per Coulomb electric field between two plates that are 3 centimeters apart? This is coming from chapter 17. Well, we know that electric potential difference, this idea right here, is actually equal to voltage. That's another way to say the same thing. And we know over here that electric fields, okay, are the capital E in our formulas. Now, we talked about this in one of the packets. We said that a Newton per Coulomb is the same as a volt per meter. That's going to be important because when we're talking about finding voltages, we're probably going to look more towards the volt per meter approach. And the last thing we're given is this 3 centimeters distance between two plates, which is a 0.03 meter distance. Okay? So if we go and we look at our formula sheet, we start thinking, okay, what are the relationships between these things? The electric field is defined a couple of different ways. The first way we talked about it was the force, the electric force, divided by the charge. Now, the thing is that tells us exactly why we have newtons per coulomb as our unit. That's what F over Q would give us. However, that's not the other stuff that we're looking for. So we keep looking. And there's another version of the electric field formula, which tells us it's the voltage divided by the distance. Okay, so as you go over a distance, if the voltage changes, there's an electric field between those 2 points. And so what we're going to do is we're going to go ahead and ignore this middle formula and just work with E equals V over D. If we're looking for the voltage, our formula can be written as the electric field times the distance, which would just be our 1800 times 0.03, which turns out to be a flat 54 volts. Okay. All right, question number 3. What is the capacitance of two plates that have a potential difference of 3.8 volts and each hold plus or minus 1.4 microcoulombs of charge. Well, if I'm looking here, this would be our voltage. Capacitance is C. And over here, when we talk about charge, charge is always measured as either a little q or a big Q. Because it says that the plates are holding it, we're going to use a big Q. It's not a point charge. It's a compilation of charge that's piled up. And so when we look at these three things, there's only one formula that connects all three of those together. And that's a pretty simple one. Q equals CV. Our charge is our capacitance times our voltage. Well, our charge is 1.4 E negative 6. Now remember, when we talk about charge on a capacitor, we always talk about the positive plate. It says plus or minus, but we're only going to look at the positive plate. All right, equals C, our capacitance that we're looking for, times the voltage of 3.8 volts. So we're going to grab our calculator, and we're going to do a division. 1.4 E negative 6 divided by 3.8. And that's going to give us a capacitance of 3.68 E negative 7 farads. Now, it looks like we're only using 2 sig figs, so this should really be 3.7 E negative 7 farads. But we talked, and so this is an acceptable answer. However, we talked a lot about trying to use prefixes in this chapter, in this unit. And so if we think about, it's really close to negative 6. To make it negative 6, I'd actually have to make the number smaller. I'd have to come back this way to the left. So I could put 0.37 microfarads. If I wanted to go the other way to make it E negative 9, okay, I'd have to go 2 spaces to make it E negative 9. That would be 370 nanofarads. So either one of those is also an acceptable answer. Play around with it a little bit. Try to make sure you understand how to make those conversions so that you can get the prefixes. It's just nice to have that. It simplifies our problems a lot. All right, next we have how much energy is stored on a capacitor. And it's got a certain capacitance, and it looks like it's given as a voltage. Well, if we think about the formulas that we're given and we start talking about the potential energy on a capacitor, we know the potential energy from a capacitor is always 1/2 QV or 1/2 CV squared, or let's see, if we got rid of the V, it'd be 1/2 let's see, it's Q equals CV. Sorry, I'm trying to remember all the formulas, and just got to remember, if you solve for V, it's Q over C. So that would be Q squared over C. There you go. Those are our 3 versions. Really, you don't have to have all 3. You just need to know Q equals CV, and then the first one. Potential energy is 1/2 QV. Just depending on what you're given, each of these has their own value. If I want to just use one formula, I'm going to come over here. This is a capacitance. That's C. And this over here, 6 volts, is a voltage. That'd be V. So I really like this middle one right here. Okay. So the potential energy that I'm going to have stored is 1/2 the capacitance of 3.5 E negative 6 farads times 6 volts. I grab my calculator. 0.5 times 3.5 E negative 6 times 6, and I get 1.05 E negative 5 joules. Remember, energy is always measured in joules. To round this to 1 sig fig, or 2 sig figs rather, it's 1.1 E negative 5 joules. If I wanted to make it E negative 6, so I can make it micro, I'd have to go to 11 microjoules. So it's up to you how you want to answer that. I prefer using the prefixes when I can, but, to each their own. All right, question number 5. What's the peak voltage in an AC wall outlet, okay, that has an average of 120 volts? And so we know that the V average is 120 volts. But we know that, remember, that voltage follows a sine wave when we use AC circuits. If we said its true average was 120, that would mean that this right here would have to be 120. But we know that there's a below and an above. You know, there's a negative and a positive. Truth is that this is 0. Okay. We also will sometimes call this average what we call an RMS, because if you do a straight average, everything should average to 0. You know, you have this point here with this point here. What we do instead when we do a root mean squared is we turn this side, we reflect it up into the positives. And when we do that, we get a new average that lives right up here. Okay? I'm just kind of reminding you of what we talked about when we talked about RMS. It gives us a higher value. Now, does that actually mean it's high? The answer is no. It's that when you say negative down here, a lot of times we would think to subtract. The negative is a direction. It's not the value of the voltage. Are there times when the voltage is 0 right here? Sure. But it's not the average voltage. We're going to say the average is more this value here. And so when we find the RMS value, what we have to do, just a second. Sorry about that. I had somebody come into the room. Okay, so we have an average or an RMS value of 120 volts. The formula that we use to calculate peak versus RMS, remember the peak should be higher. Okay, we use this V sub naught, which is equal to VRMS times the square root of 2. Now you might not know why, you might not remember why root 2 is so important, but if you think about the 45-degree angle on the unit circle, you get that root 2 over 2 approach. That root 2 is really important. It has a lot to do with that. And so we take our V naught, which is equal to 120 times the square root of 2, and we come back over to our calculator to calculate 120 square root 2, and we get roughly 169.7 or 170 volts. Okay, so even though we're running 120 RMS in our houses, it peaks up at 170. Okay. So what amount of resistance would be required to set up a 3 milliamp current given that you only have a 45 volt battery? So this is straight Ohm's law. V equals IR. The voltage is 4.5 volts from the battery. We want 3E negative 3 amps. And the question is, how much resistance do we need? So this is just 4.5 divided by 3E negative 3. And we get 1500. So R would have to be 1500 ohms. Okay. How much resistance does a 100 watt light bulb have if it operates at 110 volts? When we talk about watts, we're talking about power. That's the biggest issue that we have with this, is a lot of people forget that that's power, we have a resistance, and we have a voltage. Now you have to remember that P, by definition, is IV, but we know that V equals IR, and since I don't actually know the current, I'm going to rewrite this as I equals V over R, and that stuff can come up here. Similar to what we did with the capacitor potential energy problem. Power is now going to equal V squared over R. Okay, so with just the V and the R, we should be able to find the power, or with the power and the V, we should be able to find R. So in this case, we have 100 watts is equal to 110 squared over R. A little Welcheroo, and R equals 110 squared over 100. So we take our 110 squared divided by 100, and we end up with an R value of 121 ohms. Now, technically it looks like I'm looking at only 2 sig figs here, so this should probably be 120 ohms. But if it turns out that we did have it correct to 3 sig figs, then we would want to include that third sig fig. All right. Let me just check one thing real quick with this last question. So we're not going to have this last question on the test, so I'm going to go ahead and skip it. Okay, we'll talk about it in class, I'm sure, but we didn't do a ton with building and finding the resistivity of the metals, so we're going to go ahead and stop there for the day. All right, good luck, guys, and we'll see you in class.